We can use the conservation of energy to develop the heat conduction equation for this long, thin and insulated rod. Let's have a small point here which represents the differential element. So let us zoom in into this element. You will find this element to be a square cube where you have the dimension x in this direction. So you have a y here, and then vertical is your z. The delta x, delta y, delta z for this differential element is very small, which is approximate to 0. Since you have hot boundary condition in this surface, therefore the heat flux will flow in this direction. So on this differential element here, you can see that the heat flux will flow in the x direction, passing through this element. It will go out with heat flux x plus delta x. With that, you can measure the input heat energy from here, which is the Qx multiplied with delta y, delta z, which is this area, multiplied with the delta time, which is the time taken to pass through this element. The output heat energy is equal to the heat flux flowing out from the element here, which is the Qx plus delta x, multiplied with the area, which is delta y multiplied delta z here, and the time taken. If the input energy is equal to the output energy, then in this case, when you minus them, you will get 0. So it means that no energy will be stored inside this element, therefore the temperature will not rise. But if the input energy is greater than the output energy, then you will have remaining energy stored inside this element, which can be computed by mc theta, where your mass is equal to the rho multiplied with V, where your rho is equal to density, your volume is equal to delta x, delta y, delta z, which is the volume for this element. And then delta T is the change of temperature, which is equal to your theta. So this is the storage of heat over the time equation here. Then we can divide delta y, delta z on both sides. This term can be removed, and then we continue divide it with the delta x on both sides. So this can be removed, and then you divide it with delta x here, and you continue to divide with delta t, and this term can be removed, and you need to divide with delta t on your right hand side. So with that, you should be able to obtain this equation by taking the limit where you have the delta x approximate to 0 and your delta t approximate to 0. So on the left hand side, if you take this limit where your delta x approximate to 0, then you convert the differential equation into continuous equation, where you get the derivative dq over dx here. If you want to find the slope between these 2 points, it can be represented by dq over dx, which is equal to qx plus delta x here minus qx, which is the height here, and then divided by delta x, which is the length here. So if you take height divided by the width here, you get the slope. So in this case, since you have qx minus qx plus delta x, to make this term equal to this term here, so you need to multiply negative on both sides. So in this case, you have qx minus this, which is exactly the same with this term. So therefore, we can represent it to be negative delta q over delta x. So this is the reason why you have negative here. By using the same approach, let's take the limit delta t approximate to 0 on the right hand side. So in this case, your delta t over delta small letter t here will be converted to the derivative dt over dt here. Next, we can substitute the heat flux formula inside this, and you should be able to obtain the second derivative of the temperature. K prime here indicating the thermal conductivity, rho indicating the density, and C is the heat capacity. So in this case, if we divide it by the rho C, so rho C here can be cancelled, so your K prime over rho C actually is the thermal diffusivity. With that, we success to obtain our heat conduction equation, which can be written into this formula.